So friends, this is the numerical problem of a simply supported beam and we have to draw the shear force and the bending moment diagram for this problem. There is a concentrated moment acting at the point C here. You can see this. Now first step is to find out the reaction at the point A and the reaction at the point B. Suppose the reaction at the point B is lying vertically upward in vertically upward direction and reaction at the point A is also lying in the vertically upward direction. Now the first equation that is obtained is RA plus RB is equal to 0. That is, sum of these two reactions will be 0 because there is no vertical load acting over this beam. Now the second equation is sigma moment about the hinge, that is point A. This is the point A, about this point is 0. Now because of this vertical load, there will be a movement about this point A of magnitude RB into this distance L plus L, that is 2L, and it is going in which direction? Anti-clockwise direction. Why? Because this RB is rotating this beam AB in anti-clockwise direction about the point A, and because of this movement there will be a movement of magnitude minus m, okay, value minus m about this point A, and which is trying to rotate this beam AC in clockwise direction about the point A. So clockwise direction. So it will, why it is rotating this beam AC in clockwise direction? See this. This is the point A and suppose this is the point C, and a movement is acting like this at this point C. Now this movement is trying to rotate this AC beam element in clockwise direction with respect to this point A. That's why it is taken here as clockwise. So RB will come out to be m by 2L after solving, okay, and RA will come out to be minus m by 2L using this equation. So here the value of RA is coming out to be negative, so we will reverse the assumed direction of RA here like this. So the RA will act in vertically downward direction like this because the sign of RA is coming out to be negative. Now friends, we will calculate the shear force at the point A, C and B. For that, what we have to do? We have to find out the shear force on the left side of the point A and on the right side of the point A. Why? Because there is a reaction, RA is acting at this point A. That's why we have to find out the shear force on the left side and on the right side of the point A, because shear force will change suddenly when going from the left side of the point A to the right side of the point A. That's why we have to find out on the left side of the point A the value of shear force and on the right side of the point A the value of shear force. Similarly is true for the case B, because there is reaction RB is acting at the point B. That's why we have to find out the shear force on the left side of the point B and on the right side of the point B. But at the point C there is no vertical load acting or point load acting, only this concentrated movement is acting. That's why we have to find out directly the shear force at the point C, because the value of shear force will not change when going from left side of the point C to the right side of the point C. So let us find out the value of the shear force on the left side of the point A. For that we have to construct a section here on the left side of the point A, and looking on the left side of this section you can find that there is no force or movement acting that will contribute to a shear force about this section XX. So the value of shear force on the left side of the point A is 0. Now value of the shear force on the right side of the point A we have to calculate. So for that we have to again construct the section on the right side of the point A to find out the value of shear force on the right side of the point A. This is the section XX constructed on the right side of the point A. Now looking at on the left side of this section, you can see that only this force is acting, which is accounting for the shear force at this section XX. So because of this force RA which is acting at this point A, shown here like this is the RA acting vertically downward having magnitude m minus m by 2L. So this force will contribute toward a shear force of magnitude minus m by 2L. Negative sign taken here from this sign convention. Now I am showing why it is negative, because this force is trying to rotate the beam element which is lying between the point A and this section XX, that is this beam element, in anti-clockwise direction about this point, okay, which is passing through this section XX. That's why it is treated as negative here. Now we will find out the shear force at the point C. For that, what we have to do, we have to again construct a section passing through the point C here. Now look on the left side of this section. This force is only contributing to a shear force about this section XX having magnitude minus my2L. The explanation of the sign here taken is same as we have done in the previous case of calculating the shear force on the right side of the point A. Now shear force we have to calculate at the point on the left side of the point B. For that we have to construct a section again on the left side of the point B. Now looking on the left side of this section, this force is contributing only toward the shear force about this section XX, and this movement will not contribute toward any shear force about this section XX. That's why the value of the shear force on the left side of the point B will be taken as minus my2L. Sign convention is similar as we have done for this case, the case of point A and C. Now we have to find out the shear force on the right side of the point B. For that we have to again construct a section on the right side of this point B. Now looking on the left side of this section, this force is contributing toward the shear force about this section XX, and this force is contributing toward the shear force about this section XX. This is contributing a negative shear force of magnitude minus m/2L, and this will contribute toward a positive shear force of magnitude how much? Because RB is equal to m/2L, so it will contribute toward a shear force of m/2L about this section XX using this sign convention. Why? Because this force RB taken here, suppose this is RB acting at this point like this in the upward direction, is trying to rotate the imaginary beam element which is present between the point B and this section XX, this imaginary beam element in clockwise direction with respect to this point which is lying on this section XX. That's why it was taken as positive. That's why it will give us 0. Now we will draw the shear force diagram. Suppose this is the line ACB drawn up to the same scale. Now at the point A, the shear force is 0 on the left side of the point A, and it is going to minus m/2L on the right side of the point A, so making cross here, and on the at the point C it is again having the same value of minus m/2L, and on the right side or the left side of the point B it is minus m/2L, so again m minus m/2L here, and again going to 0 on the right side of the point B. So joining first point with the second, second to the third, third to the fourth, and fourth to the fifth. The shape of shear force diagram between point A and B is a horizontal line because there is no load acting between the point A and C, A and B. Now friends, we have to draw the bending moment diagram. For that we have to find out the bending moment at the point A, C and B. We have to find out the bending moment directly at the point A. We have to find out the bending moment on the left side of the point C and on the right side of the point C, on the left side and on the right side. Why? Because there is a concentrated movement acting at the point C. That's why the bending moment will change suddenly when going from the left side of the point C to the right side of the point C. So we have to find out on the left side and on the right side of the point C the value of bending moment, and at the point B we have to find out the bending moment directly. Now at the point A, the value of the bending moment, if we want to find out, then we have to construct a section here on the point A. Now looking on the left side of this section, you can see that there is no force acting, no moment acting. That's why the value of bending moment at the point A or about this section XX is 0. Now the bending moment on the left side of the point C, but when we want to determine, then we have to again follow the same procedure. We have to draw a section XX on the left side of this point C. Then looking on the left side of this section, only this force is accounting toward the bending moment about this section XX, which will be hogging in nature, and the magnitude of this bending moment will be equal to the magnitude of this force is equal to m/2L into this distance L into L. Okay, and the minus sign is taken because it is creating a hogging bending moment. Why? Because this force is trying to bend this beam element AC in this direction like this, creating a negative bending moment, that is hogging in nature. That is because of this hogging in nature. That's why it here taken as negative. That is concavity down. Concavity down. Okay. Now we will find out the bending moment on the right side of the point C. So draw a section on the right side of the point C, following the same procedure. Looking on the left side of this section, this force is contributing toward a hogging bending moment about this section XX of magnitude minus m/2L into L, and this concentrated movement is going in clockwise direction with respect to this section XX and lying on the left hand side of this section. That's why it will be taken as positive, denoted by plus m. Why? Because using this sign convention, if any movement which is lying on the left hand side of a section and is going in clockwise direction is treated as positive. So that's why it is treated as positive. Now it will give us the value of m by 2. Okay, now we will calculate the bending moment at the point B. Now drawing a section directly at the point B, okay, here section XX, and looking on the left side of this section, this force is contributing toward a bending moment of minus m by 2l, hogging in nature, which is hogging in nature, into l plus l, that is 2l. And this force, and because of this concentrated movement, the movement will be positive, that is m. Why? Using the same sign convention, that is, if this is the section XX and this movement is lying in clockwise direction and lying on the LHS of this section, that's why it is treated as positive. Similar is the sign convention used here. So you can find that the bending moment is coming out to be 0 here. Now we will draw the bending moment diagram. For that we have to construct a line ACB here like this, and you can look that bending moment at the point A is 0 and bending moment on the left side of the point C is minus m by 2. Okay, so here it is taken as minus m by 2, and bending moment on the right side is again going to m by 2. So going upward like this, here I am rubbing this, having magnitude m by 2, and again going to 0 at the point B. So joining A first point with the second with the third is joined, and third with the fourth is joined, we will get our bending moment diagram. Now friends, see this, between the point A and point C, the bending shear force diagram is a horizontal line. That's why the bending moment diagram is a inclined line. And between the point C and point B, the bending moment diagram, the shear force diagram is a horizontal line. That's why the bending moment diagram is a inclined line between the points C and B. So friends, this was all for today's topic, and if you like my video, you can subscribe my channel and also press the bell icon for the notification of the upcoming videos. So thank you friends for watching the video.